Welcome back to episode number 4. In this episode, we are going to be working on a problem called Read It and Weep. The description for the problem is, we found a mysterious binary lying around, can you read its secrets? And then it gives us a challenge address. And then it also gives us a binary read it, which appears to be a 64-bit executable. So just like in the previous episode, we are going to load up our file inside of Ghidra. Get a quick look at what's going around, and then we might choose another dynamic analysis approach from there. So here we are looking at the functions. We go to main. Looks like they say there's a hidden message in the binary, find it and get a flag. They read some stuff from standard in. We'll call that user data. They encode first the user data, and then they encode second something else. So it looks like what's actually happening here is your user data, they read in hex 40 bytes, but user data is like a really small buffer. So I think what we want to do is retype this so that it's hex 40, which might be a mistake there. So 16 plus 56. The reason I'm doing this is because buffer overflows exist. So I don't think that's going to be the case in a reverse engineering problem, but you know, we'll just be careful. Okay, so it looks like user data should be 48 bytes. So we'll say character hex 48, which was 72. All right, great. So we read in hex 40 bytes. We encode the first bytes using this encode first section. We encode some offset in there using this encode second function. And then it does a mem compare, and then potentially it prints the flag. So if we go into this encode first function, it looks like absolute garbage. It's doing some math, some offsets. There's a while loop. Potentially this is just a counter, although it looks like it's something in the counter is being assigned to. So yeah, it looks like it probably just goes through this hex 10 times and it does some math each time. So that's fun. Maybe we'll get a chance to use angr after all. I know some people were probably disappointed in the other episodes. So then in this encode second function, looks like we got another while loop here, and it like does some stuff up here, builds maybe like a key. I guess that's what they've named it. Maybe misleading, I don't know. And then down here, they malloc some space and go through some loop 10 times. And then in the end, if they both are correct, then it calls this read and print flag function, which requires that you have this /flag thing. So we'll make sure that we have that in our working directory. Okay, I'm ready to start running stuff. So, you know, you never know. Maybe angr will just figure it out right away. Seems unlikely in this case because of those loops, but we'll talk a lot more about why that's my intuition in a second. So the first thing we're going to do is we're going to start up, we're going to make that flag file actually, touch flag. And then we're going to start up our angr instance. So docker run, give me an interactive like standard pipe in, standard out, TTY, a new TTY. Delete the container when I'm done so I don't have a bunch of like extra stuff in my hard drive. Mount the local working directory. Type v into the /local directory in the container. You can pick whatever you want. That's just what I pick by default. And then angr /angr. It gives me a shell. Now here I am with all my stuff. Say ipython3. Cool. And so another thing we're going to do this time that we didn't necessarily do last time is we're going to make a solve script. And I'm actually just going to copy the one from the previous thing so we get our nice little hook function. Solve. And we're just going to get rid of all of this. Okay, so cool. We got an angr instance open. We got the solve script. Let's start. So it was read it. There we are. So it's like going through the binary and trying to find code and doing all that great stuff. And we're also going to set the logging level like we did the previous time we used angr. All right, so now that we have that, we're going to make a new simulation manager and we'll just start it up. Who knows, right? Maybe it'll find stuff. p.factory.simgr, which is a shortcut for simulation manager. So now we have our SM there with one active state, which puts us right in the entry point, and we can say sm.run. And all this is just gonna like step all the states until everything dead ends or exits or something. And what are we looking at on the screen here? Well, every now and again, really quickly, there's like this different colored text here. The sim manager is stepping with X many states. And then the white text is the result of stepping each individual state. So each block, like this hex 973 block, results in 2 new states. So it puts both of those states into the active cache and then it moves on. And as you can tell, the purple text is appearing a lot less frequently than it was in the beginning, because what's happening is every time we get to this 40973 block, we get 2 new states, and it's just like really getting out of control. This is not just a problem. This is the quintessential problem with symbolic execution. When people tell me like symbolic execution is slow, yeah, it's slow. There is a lot of reasons why emulation can be slow, but this is why symbolic execution is even slower, because you have this instance where one state can get to a branch, and depending on what the user entered, the branch can take 2 possible new routes. And then each of those new states get to a new branch, and depending on what the user entered, those new states can take 2 new routes. And each time we're increasing, each level of that tree, we're increasing the number of states we have by a power of 2. So really, really not good for the speed of our executing problem. But because you know now that that is the problem with symbolic execution, you know what to look for, right? So what kinds of things cause a state to break into 2 new states, and then those 2 new states break into 2 new states, and so on and so forth? Well, it's a branch dependence on user data. When the user controls something inside the program, the symbolic execution engine is going to say, well, if the user entered this, we could have gone this way. And if they entered this, we could have gone this way. So let's explore both ways. We'll put both of the options into our active cache, and we'll step both of them. And so that's the kind of thing that we're looking for. We're looking for branch dependence on user data. And I know that that's going to be the case right here in this 400973 thing, because there are like an absolute ridiculous number of those. So we have 1,024 states. That's a lot. So let's go to that address. Navigation, go to, oh, I didn't copy it like I thought I did. So we'll just say sm.active, I don't know, the first one. Wow, look at us, lucky. Okay. And we'll go there. Oh, doesn't like that. The binary in Ghidra got loaded at a different address, which I know because I can see right there. So we're just going to change the 4 to a 1, and then boom. And now here we are. We are at the beginning of this math block inside encode first. We do a bunch of instructions, like there's no branches going on here, just like a bunch of math, and then we get there, boom. And then what probably happens is we make it past that one, and it goes just a little bit further until we get here. And the reason why I think that is because this one has a branch that takes us right back up to the top there. So that's why we have so many states. They bring us back up there. Now, if I had to guess, the reason why that's happening is because we are probably, like, this local 14 variable gets modified based on the value of user data. which it looks like right here, we offset into our buffer by this local 14 value. So yeah, and then we XOR the value by something. I don't know. I'm not going to sit here and do math in front of you because we're going to let the computer do math. The computer is really good at doing math. But the problem is right now the computer, although being good at math, isn't good at figuring out like how many times do I go through this loop. And there's a paper written by Thanasis, Dave, and Alex from For All Secure called Veritesting. And Veritesting is the idea that each time we go through the loop and we get to this condition, it's possible that the loop will exit, right? So what's really happening is the symbolic execution engine is like, well, one state might have exit and the other state might continue through the loop. And then we just continue through the loop basically indefinitely. It's like, well, I can get through this loop a billion times, and then each one of those billion times through the loop, it's going to say, well, there was the chance I could have not gone through the loop the next time. So if I'm not making sense, another way that I'm trying to explain it is, let's say that we had direct control over local 14, which maybe isn't the case here. There's some math involved, but let's say it was like, while the user enters a byte that's less than 0x10. Well, I could enter the 0 byte indefinitely. I could enter the 0 byte forever and it would constantly satisfy this condition, right? Or I could enter 1 byte that satisfied the condition and then 1 byte that didn't satisfy the condition, right? So I would only go through the loop 1 time. Or I could enter 2 bytes that satisfy the condition, or 3 bytes, and so on. And so what's happening here is the symbolic execution engine is trying to reason about how many times do I need to go through this? And the answer is it could go through it a lot of times, and every single time it could also just not go through it. And that's why we're having so many states. So Veritesting is going to make it so that we merge all of the states that don't make it through the loop instead of stepping them. So every time we exit the while loop, we're going to freeze. We're going to be like, okay, this one just did something special. It got out of the loop. So we're just going to hold on to it and we're not going to step it. And then the next one, like we're going to go through the while loop again. Then the next one that exits the while loop, we're going to say, oh, this state and this state both just exit the while loop. They have the same program counter, so we're going to merge them. And memory that was dependent in state 1 and state 2 isn't lost. Like, it's just a big conditional or now. It's like memory can be this or it could be this, and it's beautiful. So, but anyway, that's probably a lot more than I had anticipated talking about Veritesting, but we're going to use it. So instead, we're going to remake our simulation manager. We'll say SM equals that. Yep. And then when you make the simulation manager, you get a bunch of options. So simulation manager question mark. And so I think what we want to do is this Veritesting equals true, which actually isn't listed here, but there's a huge list of options on the angr documentation, which is actually really easy to read. Strongly recommend it. I know it can be tough when you're starting like a new tool and you're like, come on, Tim, I just want to solve problems and there's all this documentation, and it's really tough to sit down and focus because you don't have a motivational example. Well, I have experienced that as well, but I will say that learning a new tool can absolutely change your problem-solving mindset, and it could be a very foundational change to the way that you approach things. And sitting down and investing that time up front will make it so that future problems that you want to solve, you can solve a lot faster. Like this one, for example, I happen to be pretty good at math. I have a major in math, a bachelor's of science in math. But, when I look at this problem, my first approach isn't, oh, well, let's break it apart. Let's see, how does the shift and the add play together, and how does the arithmetic rotate work? But no, I'm like, the computer's really good at math. We're going to have the computer do it. So let's do that. So simulation manager, Veritesting equals true. And so now we have this simulation manager exactly like we did before. And all we're going to do is say sm.run. And it's going to do some stuff. And I'm going to let it run for a little bit, and while that's going, we're going to talk about a different construct in angr called explore. So you can see right here that my simulation manager dead-ended, and we'll take a look at that in a second. I'm pretty sure it found the flag, but we'll talk about explore. So when you make a new simulation manager, a lot of times you're trying to get to a particular point in the code. So let's just first copy in some of this stuff so that we have it later. And it looks like this, explore, and then you can say find equals, and you can give it a lambda, like lambda x or s for state, and then you give it some condition, like, I don't know, flag in standard out or something. Or you can give it an address, like we know what address the print flag function happens in, so that seems like a good place for us to try to find. Read in print flag, perfect. Let's give it this one. We'll actually just, I'll teach you how to use symbols in angr. So we'll say find equals print flag equals p.loader dot find symbol, and then we'll give it the name. And then if it finds it, we'll get this rebased adder attribute, which is just an integer. So we'll say find the print flag function, and then we will, you can try to avoid places as well. So if you noticed in the main function, there's this other thing, sorry, that's not correct. Yeah, it's not correct, that's right. Great, thank you. So we're just going to say, and I could probably do this in a more like programmatic way, but for right now, I really just want to show you what happens. Great. We'll do our logging thing. Logging.getLogger angr. All right, great. And so our Veritesting thing worked out great. We had all these dead-ended states, but now we want the one that has a flag in it. So over here, we'll know which one has a flag in it because we made it to the print flag function. But over here, we have 3 dead-ended states. So I'm gonna tackle both situations, but it'll be pretty clear how you do it when you only have the one that you need in a second. So here's my simulation manager with 3 dead-ended states. Dead-ended is a list, dead-ended, just like the active state was, and each one of these is a state. So we'll say like 4s in all the dead-ended things. We just want to print the standard out. So we'll say s.posix.standardout.concretize. So what does concretize do? It takes the standard out buffer, and if there are symbolic bytes in it, it makes them not symbolic, and then it turns it into a string for us to see. And so this one was that's not correct, that's not correct, here's your flag, and then nothing because our flag file's an empty file. So what I'm going to do, so this would have gotten you the flag if we connected to the server and we sent it whatever values. I'm going to show you how to get those values in a second, but first we're going to make this flag file have something more interesting in it. So we'll say echo haha into the flag. Okay. Now we're going to go over here where we did our explore. We're going to hook locals. Okay, and then let's run our script, solve.py. Do our Veritesting trick, which is a lot faster than the not Veritesting. Veritesting is a very intrusive exploration protocol, and it doesn't always work. So maybe you're wondering why it's not on by default. It's probably better that you try without it first for speed and also accuracy. But anyway, so here we have our simulation manager with 2 active and 1 found. So one of the places got to the flag. So sm.found of 0, So that gives us a state, s.post6.standardout.concretize, and there's our flag. There's a hidden message in this binary, find it and get the flag. We entered in some stuff, correct, here's your flag, and then just a new line. I think that's because we actually stopped before we got to the interesting stuff in here that prints flags and whatever. But because you're supposed to be interacting with the service remotely, it doesn't actually matter that we can't see what we put in our own file locally. You have to send data to the server. You might be like, well, we know what the program says back to us, but we don't know what we're supposed to say to the program. And the answer is, well, yeah, actually we do. We just go to this POSIX object and we say standard in, and then here it is. The secret code is, I don't know, some garbage. And this probably isn't even correct because as you can see here, there's like unprintable characters in there. And that's not great for us. Maybe it'll still work. In fact, it probably will still work. But what we can do is we can limit the standard in to only be printable characters. And we can limit it to a certain length too. Like you see, like there's this like weird @ symbol here and these bytes randomly after a null byte. Maybe the server actually terminates on a read that wasn't properly emulated or something. So, Ranger, you're interrupting my video. Okay. So now we're going to add those assertions. So before we actually do anything, we're going to pull out our state before we actually explore here. This is when we start stepping and whatever. We're going to pull out our state, which is sm.active of 0. We're going to make some assertions. We're going to say, we're going to make a, I think actually we'll do this before the simulation manager, and then we'll entry state, and then we'll pass it in. I'll show you why in a second. So we just pass in our starting state right there. And so if you do this entry state function, you can actually pass it standard in equals some buffer. So this is a good time for us to talk about clarify. So in clarify, we can make bit vectors. We could say user data equals clarify dot bit vector symbolic. You have to give it a name, which doesn't actually matter for anything for you. It's just when you're debugging and you're looking at how the symbolic execution engine built its big equations for like how to go different directions in branches, this is the name of the variable it's going to use when data that you're passing in this variable is referenced. And you have to give it the number of bits. So let's say, I don't know, the secret code has to be like 20 bytes. I'm just pulling that number out of my butt. I don't actually know. But this secret code is probably fixed. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we need probably maybe more than that. We need maybe double. So we'll say like 36. I don't know. Okay, 36. Great. Standard in equals user data. Okay. And then now we're going to run our thing again, and we'll also extract this state at the end, sm.found. If not, sm.found. So if we can't actually find anything, then we're just going to print like, and then, I don't know, book or something. And then otherwise, we're good to just do this. So we found one state. We'll say e.post6.standardin .concretize, and we'll print that out. All right, and then we'll run our script again. Watch Veritesting do its thing. Except this time the input data is like some buffer we made, and I don't expect there to be anything different other than the fact that the length of the buffer is now limited. We're going to show how to make it only printable next. So here now we have what seems to be even like worse garbage than before. Secret null byte code, null byte is something, yada yada. Okay, wow. But now we want to make sure everything's printable. So what we can do is we can say for I in range 36, which is what we made it, user data len equals 36. we'll say user data dot get byte I. So this goes through big endian, each byte, and we want to add a constraint to it. Say s.solver.add. So this is how we're going to add constraints to the solver, and we want to make it so that this byte can only be printable. So to start, we're going to get this string. Maybe we'll say like from string import printable. So these are all the printable characters. Oh, jeez. Huh. My keyboard's weird. And then for each of them, we'll say, yeah, it has to be a printable character. So equals X. So X is going to be each of the printable characters. So we have to loop over those as well, which is a bit annoying. So instead what I'm going to do is I'm going to use clarify.or, which is going to let me like or a bunch of statements together. So I'll say clarify.or equals X, and I'll say or X in printable. And then we're just going to unpack all of these conditionals into this OR function. So what's going to happen is we'll take the first character from printable, we'll assert that the byte equals that. We'll take the second character from printable, we'll assert that the byte equals that. And that's going to make us a big iterator, right? And this unpack thing is going to make arguments. So the first argument to OR will be this conditional where X is the first value printable. And the second argument will be the second, where this is this conditional where this is the second value in printable. And then we'll add that as a constraint. So this byte has to equal anything in printable, basically. Wow, okay, that's a really small amount of code, but it's going to generate a lot of constraints. And then we'll try again. So one thing that I'm worried about with this is that normally at the end of your string you put like a null byte or something, but apparently it didn't actually matter. So it says our secret code is this string. So let's try it out. I don't know. So here's the standard in. It's not just like this little bit at the end there. It's like this whole thing. So we say dot slash, what is this? Dot slash orig read it, and then we'll pipe in this. Yeah, I have to put a pipe. And then it says, correct, here's your flag. So we just took the output, the standard in thing, we piped it into the program, and we got the fake flag that we put there. Okay, well, I think that will do it for this episode. I look forward to seeing you next time. Goodbye.